idea. And booze.
Yeah, why would you do that? How do you go motorcycle hunting?
Well, you can tell, can't you?
Yeah. Well, I think you bring your helmet in a couple times.
Yeah. Yeah, I'm not going to be riding it too much longer, I'm telling you. After that one spill, that's it. Yeah, that's what all this is. Like, it's actually all over the side of my body.
Oh,
Yeah. So,
when did that happen?
about
A week or two?
4 days ago.
Wow.
And I slid across the pavement for a while. Like, the back of my helmet is just completely off, so.
Oh my god.
Yeah, I'm glad I was wearing a
How
helmet.
did that happen?
Huh?
How did it happen?
My front, what happened is I had no front braking, and for some reason the brake stuck. And if you have no front braking on a motorcycle, you only have rear braking, you'll fishtail.
Gotcha.
And so I only had my rear brake in downshift. I tried to downshift as fast as I could because the light on University, you know where Daisy Dukes is?
Yeah.
It turns real quick, and I was about probably a couple feet, and the car was anticipating and came right in front of me, so I just split it.
Oh my god.
And I was wearing t-shorts, shorts, and like
you got all messed up.
flip-flops and crap. It was a bad idea. It was the only time I've ever done that too. I was like, go figure. And the best thing was, I was planning on taking it down to a fire that day.
Oh, so much for that idea.
Yeah, and then
You're pretty messed up.
no, the engine guard a little bit scratched, and the pedals were not under the floorboard.
Just one side.
But honestly,
Up.
you can't even like tell. And like I told one guy, and he's like, "I'll take a look at it, and maybe I'll get close to what I wanted, but probably not." It was pretty significant when that happened. But fortunately, it could have had a lot more damage than it did, though.
Yeah, you could have had a lot more damage.
Oh yeah, that's true. I could have been in the hospital right now. But luckily, I had my backpack on, and that's what saved me. Otherwise, I'd have second-degree burns all over my back. So.
That's crazy.
That's why I came in one day and I was just like limping, and I had long sleeve shirts on, and I was just like hunched over like this.
Crawling across.
Yeah, that was the day. And Jeffrey's like, what the heck is wrong with you? You're like falling asleep. I hadn't been in a motorcycle accident. I was just hunched over in pain. I'm sorry. I'm sorry, sir.
I don't know. I don't mean anything I say ever.
I watched the body lectures because I wasn't here. It was one of the most entertaining lectures.
Oh my god, yeah.
That's what I'm here for.
I'm just sitting there because I've been here at NDLR and I hear him just wearing out everybody. I'm just like, oh my god.
Yeah. I don't think I'm wearing people out.
No, Blasingame. You and him just go back and forth.
Yeah, that's pretty much all lecture. And then also you use like 8 bucks or whatever.
Okay, that was not my fault. That was not my fault.
You paid what?
for 4 pieces, like $80. That's so funny. You guys see the revised schedule?
Yeah, class today, twice, class tomorrow, twice, and Wednesday once.
We want more and more of his time. Because it's like squeeze and sulking. Hold this is retired, lead it somewhere else. The guy's the best professor here, period.
Yeah, but some of us also work jobs, and it's very hard for us to be here.
There's a thing there.
You can walk in, start logging in, and then go up to my office and get a drink.
Good noon, Tom.
What's wrong with you? Good point. Okay, so I need to run upstairs and grab a drink because I was over at a meeting with Civil. We'll be right back.
Right on.
man.
Oh.
Talk to me.
Oh my god. This is like a rookie, man.
You're in a row, like talking about tests. I don't think it's a good idea for me to follow.
No, you should. You should go.
No, I should, but that'd be very immoral and very, very bad for me as a human being.
not to share with the class, and then we all, you know, take part in the evil.
I don't think it's a distributed system. I'm pretty sure it's additive.
Is it better to have a test or an assignment?
Look,
I don't know. I'd rather have a test, because then you have it within that class period, but the assignment might take like 3 weeks.
Yeah, that's what I'm saying. Just,
it depends on how hard you're willing to
if
work.
you
If you're not willing to work, then a test. If you're willing to work, then an assignment.
Yeah, I've
But no
never
one-
had them before now, so.
But the thing is, he demands far more in assignments than he does on tests.
Yeah, that's right.
But the problem with that is you never know what to study for. So
Right.
if it's like a really short assignment, then that's the best.
Which I don't think.
Like an assignment with like a 2-day deadline. Then he knows he can't get too much, but then you have time to study for whatever the hell it is he starts
Wait, I
throwing
mean,
away.
the model's been stuffed into a week and a half, so it's.
Yeah, but technically,
Very
in
quick.
graduate school, anything that has been physically assigned or electronically assigned, we are responsible for. So technically, he has 350 odd slides of material that he can do whatever the hell he wants with, you know? Plus
All
everything
the more
else.
reason though, it's a short time and
Yeah.
material you don't even go over is.
He has 150 megabytes worth of stuff that he can, like, give test questions on, technically.
Yeah, I'd almost prefer the test because he said he would just give us the equations and all that if he had the test.
Yeah, but that's a little bit unfair for those of us who haven't had, like, pressure performance.
Yeah, but if it were a test, I feel like he would make it to a point where, you know,
You
someone
can do
who's
it.
never had exposure to this
Yeah.
stuff that's only had 2 weeks would be able to.
That's
I
purely
would
speculative.
hope so, yeah.
That's purely speculative. I think he's way too smart and he's so beyond us
He is.
that anything that he tries to make easy will just be not easy. You've had those kind of professors before. I don't care where you went to school. Like, everybody has had that professor, that one professor that we can all name off the top of our heads, who tries to dumb shit down, but it ain't dumbed down. I know.
You take your medicine?
Yeah, say bad things about you.
Maybe you should. It's taking so long on the profile. I mean, I should come in and run it back up again. It's been running the whole time, right? This. If this doesn't work right, I may turn the computer off and on and have one of you log into it. Although that might not be a good idea, because I guess the way Echo works is it picks up whatever's being projected. It's in the background. It's not tied to my account.
No, I think it just records the computer screen.
Darrell said lockdown when Teams account didn't work, and I'm not sure.
Let me ask Ted real quick, out of curiosity. Hopefully it will resolve itself by the time I get back, but, I mean, it should have already finished.
We're missing some people.
I wonder why.
Lectures of
Yeah.
the week.
2 of them are out.
No, I really don't.
What's everybody's name again? Yeah.
Oh, okay. But it is just.
Yeah, names, everybody's names.
You don't know by now?
No, everybody knows me. I don't know last name.
He calls everybody.
Yeah, but I don't think that's it. Yeah. No, it's okay. I'll learn it today. Call some people, but keep it quiet.
Good. It sucks, man.
Still in my
Still not having a little bit of the family bring home with that there. It's 8 to 10 this evening.
8 to 8 today. Tomorrow is 8 to.
Tomorrow's 8 to 10. Okay.
What? Aw, we didn't have No, I intend to read it today.
I'll sleep at night.
Don't worry.
Go back to the office.
Wouldn't it sound nice?
Yeah.
It's just crazy to put that this Wednesday.
Really busy.
I'm really just surprised you picked it up. It depends on how much. People are long. Well, yeah.
You know what I've noticed?
That the lectures.
There are more white people than there should be here.
Oh, I guess I just want. I know it's a shame.
Yes, no?
Yeah.
They said it's running slow everywhere.
Oh.
Is anybody logged in fresh off of the machine today? Yes? How long did it take?
It's normal time, but that was at like 8:30 this morning.
Blackboard.
Hmm?
Blackboard.
It won't be recorded.
There's two screens, though. One that records you as you're standing there, and one that
But they wouldn't be able to see what he was doing.
Let's give it 2 or 3 more minutes, and if not, then I'll use the finger. Restart. So Sam, number 1, what'd you do this weekend?
They kind of slept about 20 hours yesterday.
you
You
would
know Mr. Whiting, he was a faculty member here, and one time he said to us in class, he had a way with words. He said, you know, I've noticed that idiots and geniuses both sleep 14 hours a day. I also noticed that when I look at them, I can't tell the difference between them. And we were all, where did that come from? He was also someone that, he would always ask questions, rhetorical questions, and somebody in the class one time said, Mr. Whiting, I have a question. And he goes, son, I live for questions. My whole career has been about nothing but questions. I can't think of anything more I'd like to do than hear your question. And he asked it, and he goes, in 50 years, that's got to be the stupidest question I've ever heard.
What was the question?
I have no idea. And then he had a game that he created for the economics class, which was playing the stock market. And somebody goes, I really think this is unfair, Mr. Whiting. You know, the rest of us don't have experience in the stock market, and others who do have an unfair advantage. And he goes, son, if I had my cello, I'd play it for you. And the student goes, I don't understand. He goes, life's tough, shut up. These personalities, man, you can't get away from them. Okay, countdown.
What?
5, 4, 3, 2, 1.
Happy New Year.
All right, Dennis, you're going to log in under you, since we know yours works. So I'm working with this guy in the education project, and the Portuguese name of Dennis is pronounced how? I don't know. Anish? So that'll be your new name.
Food from local.
Ectoplasm. So how was that 20 hours of sleep?
Well, just exhaust the first 10 hours, then I try to adjust my sleep schedule so I have to sleep at night.
But it's daytime.
No, well, the first
I'm just,
Yeah, whatever.
I just want you to snap. You know, my goal is to be murdered by a student.
I asked for it.
Yeah.
You'll be-
Actually, I want to be shot by a jealous husband, but I want to be 103 when it happens.
Nothing wrong with
Really? I thought you guys valued your elders. No?
Yeah.
So, you know.
Back in the day.
I won't be valuable when I'm 103?
Oh, no. The fact that what you would do to get, you know, shot by a jealous husband.
Hey,
Who's also a student.
sorry?
The jealous husband is also a student.
That would be pretty sick, but yeah, I like that.
So that's why you're in graduate department.
Well, what was the old joke that the 90-year-old was marrying a 20-year-old, and they said, you know, the stress of this relationship, you know, it's really terrible. It could cause death. And he goes, I see your point, but if she dies, I can always remarry. What are you doing with these fancy iPad thingies?
Your class, right?
Oh, yeah? Is that a sign?
Yeah.
It's got a point on it.
This is the one we just tried.
Mine had like a blunt end. Does it work?
Yeah.
What's the tool?
Acrobate, Adobe.
Speak English.
I don't know which name it is. I annotated something.
Send me the link, please. You promise?
Yeah.
Don't make me come track you down.
I will do it right now.
This does not look good.
Oh, no, you won't have to.
Can we just go to another room?
No, because this is the only one being recorded. That's a good point, though.
I mean, you could just.
Okay, let's see if he comes up. If he does, we're okay. If he doesn't,
Okay.
Which country is Blasingame from?
oh, let me think.
No, not you, but the name. You're from Louisiana.
It is just a Huguenot origin,
Cuban. No, French.
but it is actually English. And
The invasion during the country you work with?
the other side of my family is French. What happened to your elbow there, buddy?
Motorcycle accident.
It's why he was sleepy last time.
Yeah, that's why I was hunched over in pain.
Did you forget your password?
No, I'm probably using the wrong username.
Yeah, there's a stock.
You know, I'm not the smartest guy on the planet, but I do remember my username.
No, I keep on getting confused between the two usernames that you keep on using.
I keep forgetting.
Yours should be fast. You don't have 10 gigabytes.
Yes, he's got a small profile. Look at us. Small, not small.
Like a German and a Frenchman.
I really don't know what to do with that. Okay, so I can just start deleting things, right?
Yeah, absolutely. I've been on backup software.
Okay, so all the videos are up to speed now. I even put my 324 videos back on, and I will not be fired by you guys looking at my 324 videos. All right.
The undergraduate classes are recorded?
I did. Actually, I had the videos from 2007 or 2008, and they were excellent, but somehow we lost them. I don't know what happened to them. But you got it. Where's the start bar?
Oh, go down to the bottom of the screen.
He did that weird thing.
Yes, that weird thing. What do you use for your browser?
I have Chrome and Firefox on there.
The Chrome's not even on here.
I don't know if it's going to be on the desktop.
Have you ever stopped to think how unhelpful you're being?
I tried it before.
There's Firefox.
Try to flow from that left.
Rainbow, I'm gonna use what I know. Have Explorer. This is no longer fun. So we're all on the same page. You know how long it's been since I used Firefox? I'm staring at it right here. Happier? Let me put it this way, the happiest day of my career is when you're no longer in it. Nah. I was telling my wife how you were the only person I knew that could spend more money on pizza than her. Is it coming up? I did click it, right?
Yeah.
This is like a comedy. Come on. I wonder what the deal is. Did you guys notice anything slow this morning? I noticed I had a really, really, really bad connection with a remote connection. When I logged in from home, it was like this. It just took like 5-10 minutes before it even connected.
Perhaps they're doing server things.
Yeah, perhaps it's like somebody is attacking it.
Maybe the nuclear engineering department, but
I was thinking of a cyber attack.
yeah, to steal nuclear secrets, but other than that, other than the nuclear lab here.
Is there really no connection between the brain and the house? I mean, it's just a direct pipeline, right?
No, I mean, nuclear secrets, you're gonna hack something, you hack that.
I'm trying to use the word hack around me. Alright, so I need to go fetch this stuff, right? Can I get this C drive from here? Hot dog, I'm done.
Oh, wow.
Where'd the file folder go? Why didn't it stay up? Dennis.
I don't know. My profile is weird.
Sorry, Denise. What year were you born, Chip?
89.
That was the last good year of my life.
You like the Cold War?
No, the last year I was a kid. Okay, preferences, general settings, is that what it was? Yeah, never. Never. You guys had enough of me yet? What slide did we leave off on, Sam, number 1?
59.
You wouldn't lie to me, would you?
You know right away. Be careful.
I was 58. Or, sorry, 60. hate most of all. Stupid bar. Okay, so 58. And we talked a bit about how to do pressure profiles. Is this going to be on the test? Sam, number 2, favorite cartoon character?
Goofy.
Yeah.
Thinking it's good, the right answer is just sending Sam, it's already.
No, that's me. Remind me again your name.
Abhishek.
I knew that. I'm going to call you something I can remember. How about AB?
Hi.
What does your mom call you?
Abhi. Yeah.
I knew it. Favorite cartoon character?
I understood. Yeah, lots of mine.
I don't see the connection. Favorite?
Godzilla.
Dracula?
Godzilla.
Oh. Godzilla.
What the cartoon one?
Yeah, must have missed that. Boys?
Stewie Griffin. Family Guy.
Oh. Stay away from me. My son quotes Family Guy.
Daffy Duck.
I can see that. Speedy Gonzales. Little joke.
I know. Bugs Bunny.
Okay. What was Speedy Gonzales' cousin's name?
I don't know.
Slowpoke Rodriguez.
Very good. There's probably 3 people within a mile of this place that know that.
Favorite cartoon character?
Scooby-Doo.
Scooby-Doo. Dennis?
Jerry, from Tom and Jerry.
That hurts. Mr. Zane?
Yes, sir.
Favorite cartoon character?
Superman.
Right up there with Godzilla. I really hadn't thought of him as a cartoon character, but thank you. My favorite cartoon character is Woody Woodpecker. You guys know Woody Woodpecker? Yeah. So is this going to be on the exam?
Is there an exam?
Sorry?
Is there an exam?
Or on the evaluation device? Mechanism device. I prefer to use a device on you. Okay, so what do you think we're going to have on the exam? And I will send out an email on this. If you were me, what would you give? And don't say nothing. I've already had some of those emails. Yes?
Diagnostic for medical.
Ooh, ancient Chinese secret, huh? Good idea. Sorry?
Yeah, sorry. Saying give us a bunch of curves, find porosity, find the skin.
Porosity?
Sorry,
You're
permeability.
still in well logging class. Do I look like Dr. Schechter? Do you ever believe you would confuse me with Dr. Schechter?
Yeah, you're both from the south.
No.
I'm not from the same planet, though. Omar, since you're starting to read me like a book, what do you think we're going to have?
Pressure buildup.
And
Maybe interpretation.
there will be one PTA problem and there won't be one production analysis problem, as a minimum, right? Now, there may be 17 parts in each one of them.
So how many pages roughly do you?
Envision?
30.
I don't know. Paper's cheap. I got a great damn thing. Alright, so now let's talk about pseudosteady-state. We talked about steady state, and on this diagram, although these are transient, these lines are parallel. So as I told you, this is analogous to succession of steady states. That's how transient flow was described whenever people first started deriving it. But there is no such thing as steady state. Can somebody tell me on this graph where steady state is? Give me a ruler, Jim.
Can you make it show that the bar state also got?
How do you do that?
Click on the Firefox, it's yellow for whatever reason.
Do what?
Click on the Firefox and close that orange window. And then
Okay.
take it down.
And it will disappear and go away forever?
It's not there, no.
No, it's the preferences
I
on
got a
bar
better
itself.
idea. Yeah.
Preferences on bar itself.
ones don't know.
You can thank me later.
That's it, so
Hmm?
okay.
Oh, but
I think we'll go away now. I'm a classic guy. Okay, so, can somebody on here tell me where steady state is? What I told you before was this behavior why isn't this drawing? Jeffrey, what have you done?
Would it be at 2,000 PSI?
So this would be a steady state tie line, if you want to think about it that way, because the pressure is governed by this linear trend, and we know from steady state flows that's what that looks like, right? So there are a succession of these like this. And each one of these would be a succession of steady states, okay? As we progress out. So can someone tell me where we have steady state for this given system? Yes.
I would say right before you hit the complete pseudo-steady-state
Exactly.
and right after you.
It would be this point right here, and I did draw it slightly below. It would be connecting that corner with the wellbore line. Sorry, my line is not very good here. Something like that. So, and of course, that point would be fixed, and that point would be fixed. That would be the definition of steady state. How long does it last?
About a second.
Yeah, that's it. Very good. You got this down. So there's no such thing as steady state. There's either transient or pseudo-steady state. What happens after this? For an A in this course, then, and you never have to come back, and you never have to see me ever again.
So the reservoir only 3,000 feet and it doesn't go.
Right. Okay, so that's what pseudo-steady state is going to look like? This succession of steady state. I mean, what's your background?
Petroleum engineering?
From IIT?
Sorry?
From IIT?
No, from Martian Technology
Right.
Institute in Pune.
Yeah, the one with the swastika.
Sorry?
The one with the swastika, the emblem, the good luck emblem?
Yeah. Swastika.
Yeah, when I was an administrator, the first time I got the what do you call it, the transcript, I almost had a cow, but then I realized that somebody borrowed that from you. Sorry. It's a good luck symbol. Okay, so mathematically, what did you learn? Why are you taking this course if you already have a petroleum engineering degree?
Because in summer this is the most expensive, like comprehensive course I will find.
Okay. Next time before you make a decision like that, come see me. I'll find you something really miserable. I will elevate your expectations. Okay. So since you already had this, you know this is not pseudo-steady-state. What has to happen at the edge? What's the pressure derivative definition at the edge? Dennis should have known this. What is it?
Zero.
It is dP dr FRE is equal to 0. Is this 0, this gradient? What should it be?
Should be 0 at
So 0 is horizontal, right?
positive.
Just that little bit. You know, how come This is only out here at the edge.
Something to do with the boundary effect.
It is, of course, that's why the radius, or the condition, the outer boundary condition is equal to this. But I'm saying, why is the tail, why is this little piece only here? See, these are flat, and I wish I had a black line. This is flat, so that derivative is equal to 0. Where do you wish you were right now, Neil?
Someplace that the answer is staring at me, maybe.
Yeah. So do you have, are you like a beach person? Probably not. Yeah? Okay, so you're having a tropical illusion.
Yeah.
Okay. So this is actually an optical illusion. Because it's a logarithmic scale, this part is really limited to only the very outer part, but this is what? A logarithmic scale, so it really compresses the living daylights out of the big numbers, and it expands the little numbers. Okay? So these lines are actually parallel curves, but you can't see that in this rendering. I'll show you some cases in a minute. It's semi-log x-axis, so it doesn't look right. Okay. Tell me the condition that has to be met for this. Then Q is equal to That's the constant. That's the definition of pseudosteady-state. If it's not constant, what do we call it? We call it boundary-dominated flow. Does the pressure have to be, or sorry, does the rate have to be constant? Not exactly. What does not exactly mean? It still works, but the condition is not exactly met. The condition that the pressure in all that these lines are parallel is not met. If this were a constant pressure case rather than a constant rate case, all the lines would converge over here like this, but they would still have the tail like this. So is it really pseudosteady-state? No, because pseudosteady-state, the definition is that the pressure at all points in the reservoir changes at the same rate. And obviously that would not be true at the well. But out in the far field, it's close enough. Yes, sir. Comment then? Since I'm using your account? No. Good, I like that. No comment. You guys remember Fat Albert? The cartoon? Remember whenever he said, "You're like summertime," and the guy said, "How's that?" And he said, "No class." All right, Abby, you ready? This is the condition. The pressure at all points in the reservoir changes at the same rate. They're parallel. The distance per unit rate is constant. It drops the same everywhere. Is that really possible, Sam number 2? You don't think that happens in practice? It only happens in books and computer programs. How did I lose the scroll bar again? Because it's there. All right. So Sam, number 2, if I took your word for it that doesn't happen, then that would imply that the reservoir is in this flow condition for 99% of the time. Is that true? You never think about it this way. It's the opposite. The reservoir is in this condition probably less than 1% of the time. for a conventional reservoir. For an unconventional reservoir, it may be a lot different. But for the sake of argument, where you can, we're talking about 1,000 hours. How long is 1,000 hours? Quick, come on, tap. Okay, it's a little bit more than that, but it's right order of magnitude. So what are you going to do with 1,000 hours? That's 1 month. How long is the well typically on production? 50 years. Let's make up a number. So 50 years times 12 is 600 months, 600 to 1. Is that less than 1%? Yeah. So practically speaking, transient flow is short-lived. The rest of the time we must be in another regime. Okay. And that regime that we call boundary-dominated flow, what does that mean, or pseudosteady-state? Well, it means what's controlling the system? The boundary. Okay. If that's true, Dennis, make me a logical transition, an inductive comment. Transient flow is a function of permeability. The speed of propagation of this front is a function of permeability. You know that, okay? Everybody's okay with that? What is pseudosteady-state a function of?
Gravity radius.
Volume. Okay, and transient flow? It equals a function of, okay, porosity, viscosity, permeability, compressibility, but the biggie is permeability. Okay. So now you just got a quick and dirty lesson on what controls what regime. Transient flow, permeability. Boundary-dominated flow, volume. I'll repeat it. Transient flow, permeability. Boundary-dominated flow, or pseudosteady-state, volume. Can you get volume from transient flow? Yes, no, or maybe? No. Can you get permeability from boundary-dominated or pseudosteady-state flow? Yes, no, or maybe? No. It simply doesn't work. Anybody who tells you differently doesn't understand the fundamentals. Now, you can cheat, and you can use the radius investigation equation, and you can say, at 1,000 hours, the radius is propagated to this, so I've drained this portion of the reservoir. How much does that buy you? Not much. There have been numerous attempts to try to characterize the drainage radius in such a way where you can use it as an estimator for volume, but that is a bad idea. Transient flow, you should not be trying to estimate volume. Let me ask you a real quick question. I'm going to regret this, aren't I?
If the data from the transient flow portion is not very good, is there any way to recover the information that you should have gotten from that?
That's a really good question. You're saying that if you don't have transient flow data, can you still estimate permeability? And people try to do that every day. Whenever they run a pressure transient test and they miss the important part of the test, they try to reconstruct it. What you're going to find out is that we're going to utilize a lot of data in pressure transient analysis. I'm talking about high frequencies. There'll be a lot of data points, hundreds, thousands, maybe millions. But then what happens is you turn around and you come back and you go look at production data, and I told you get only 1 point a day. If it's high permeability, is 1 point a day sufficient frequency? No, because the transient's already passed. The transient's passed, it's passed. It's like taking photographs out on the highway. If something's going slow enough, you can, leave your camera on and catch it. But if something's going lightning fast, if it's faster than your shutter speed, you missed it, it's gone. Or if you took your picture at the wrong time, it's gone. That's what's so clever to me about the, what do they call the Google People View, right? Is, how they just happen to catch my neighbor riding his bike, you know, or Street View, sorry, thank you, yeah. And then they have to go blur them out, because they send them a note and sue them. I like the fact that now they're blurring out signs so you can't see what's on them. Did you guys see that now Google can see through clouds? Yeah, they've got a new product out where they can reconstruct the image below the cloud. I'm sure they got it from the NSA, right? Okay, so the question at hand is, let's say that we have this point and we want to, this is our wellbore, and I'm going to turn on smartness, I just want to know the color of that. Okay, so like black is it. Alright, we'll just use black. Alright, so we have a radius of investigation that's propagating out. RFT is proportional to square root of permeability and square root of time. There's some other stuff, we can put a constant there, okay? The actual drainage radius of the system is here. So until this encounters that actual drainage radius, you're calculating a transient radius, may or may not represent the volume of the system, et cetera, right? Okay, let me ask you guys a stupid question. And this is not meant to challenge your intellect. I want to delete the whole thing. Okay, ready? So we've got a wellbore, and we've got a finite radius around it. I want you to think about this like this is K1, and this is K2. This is not right, but it's how I want you to think about it. So the interior region has one permeability, and the exterior region has another. Then what's going to happen is that there will be a speed of propagation here. And then there'll be another speed of propagation here. If in fact, you know, you can pass through this boundary. Let's say that this boundary is kind of fuzzy. It's an interface. This is something, when you guys were talking about volume, this is something I tried several years ago. I wanted to understand how, for example, in tight gas, the reserves appeared to continue to increase. You had a signature that said it was boundary dominated flow, but yet over time, and I mean long time, like the first year, you could calculate that you would encounter boundary dominated flow, but in year 8, you actually appear to have a higher reserve than you did in year 1. How can that be? So I'll make a quick plot that if we were looking at the calculated reserves, we'll call it EUR, that it actually was drifting up this time. How can that happen? It should come down. It should, or it should stabilize, I should say. Maybe it does like this. I don't know. I'm making that up, so don't. But I noticed this was happening. So I gave this problem to a student, and I said, I want you to calculate this secondary propagation so we can see if what we're really seeing is something like this. Oops. This is up to R1, and this is greater than R1. I was thinking something like that. Now, before you guys go off on a tangent and think that it is actually real, I'm making this up. I have no idea whether this is what's really happening or not. The same thing is happening right now in your multi-frac horizontal well with what? Can I just do control roll here? So in your multi-frac horizontal well, we have this horizontal well that looks like this, and we fracture stimulated. Every time I say fracking, that's more pizza, okay? But not at Jeffrey's price. I'll be going to Walmart and buying a bunch of day-old frozen pizzas or something. All right, so we have fracture stimulated this horizontal well, and now production starts. And of course, the first kind of regime that occurs is linear flow into the fractures, and that's very nice, blah, blah, blah. Okay. What do we call this region around the well?
Stimulated reservoir.
Right, this is the so-called SRV, spur Lalone. And Ola, not my student, but a nice guy. Meyerhofer, never would have been my student. Okay. And so we usually draw some sort of a shoebox around it. What company do they work for? Did they work for? Sorry?
Exxon?
No, good guess, thank you. They work for Pinnacle Technology. Who is Pinnacle owned by? HAL. When's the last time you drove on the Beltway from 290 to the airport? Their office is on the side of the highway there. Okay, so they call it the SRB. What does Schlumberger call it? Well, they're not going to call it the SRB, are they? Actually, they probably do. But Schlumberger instead, they came up with an idea, and I guess I'll try to bring up the ink pad here.
What does SRV stand for?
Stimulated reservoir fauning. Sorry, I didn't mention that. Thank you. Okay, so what happened is that, of course, they've been marketing this for a while. And Schlumberger came along and they said, we're going to put these little pods here, and we're going to call this PR or something like that, enhanced permeability region. It didn't last, it died. Something like that.
So if we're presenting anything at a conference with this
No,
concept,
I'm joking. Everybody calls it SRV.
No.
You're okay. All right? And then they put these little pods like this around this, and they created some modeling protocols for that. And Tom decided that it really should be called the SFV, or the SFR, Simulated Fracture Region, because that's what it really is. Now, of course, I've drawn these fractures as planar. Sam, number 2, what's the possible? Your background mechanics? Math, okay, even better. What's the possible? It's supposed to be planar, right? Like that. What could it be?
Fractures?
Yes.
Could be anything.
Could be a Buck Rogers lightning bolt. Could it look like that?
Yes.
Could it look like this?
Yes.
Could it look like this? Anybody else? A company called Stratogen, which is a spin-off of Pinnacle. It was their reservoir engineering division. When Halliburton bought them, they didn't keep the reservoir engineering part. Okay. They had this thing that looked like a series of devil hooks.
that doesn't look,
Something like that. Well, what their point was is that there were existing fracture planes. When you look at rock, in the geologic setting, there's fracture planes, so they thought you were reopening. Who hasn't talked today that wants to say something? Sam, number 1?
Yeah.
I kind of went off the deep end here, right? Yeah, thank you. You could have said, hey, buddy, this is the introductory class. That would have been nice if you'd done that. Anyway, we're going to progress on here for a second. So this thing now expands, what do we call it when something expands in pressure transient terms? Call it propagating. So the volume is actually getting bigger with time.
Is that through production?
Well, the real trick here is understanding what this stimulated reservoir volume looks like. I've drawn a box, but when you look at microseismic, it might look more like that. And then Pinnacle invented a way of drawing a box around it. I mean, this is all just sales stuff. So that's what their SRV looks like. We really don't know. And so my point is, there's a whole bunch of things that it's a combination of. It's a combination of permeability, it's a combination of brittleness of rock, it's a combination of any pre-existing fracture planes, it's a combination of pre-existing fractures, it's a combination of the fluids, it's a combination of the fracturing fluids and how they reacted or didn't react with the formation, etc. But at some point we create some disturbed region, and I know you know what that means. Nobody's laughing except us. Okay, so you created some region wherein you now have a conduit to produce fluid. What I want to know is, what does this thing look like, you know, over time once you get beyond that? And by the way, the blue outline may take 25, 30 years. The red one will take another 100. What do we say in Spanish for something like this? Madre de Dios. Okay. The first time I saw a simulation study on this was a very capable young man from a near super major company. They do have gas stations, but they're thought to be an independent. And it took 250 years for the wells to interfere. Now, obviously, that assumes that they're not in hydraulic contact with each other from the fracture. 250 years. 250 years. What number do you report to the bank as your reserve? Abdallah?
Should be the next.
Is it this one? Or is it the red one?
I think it's whatever you can get your hand on during that year, and then it gets updated every year. That's my best guess.
Okay, but this is going to take 25 years to get to. This will take 100 years. What's it going to look like at 1? I'm a jerk. At 1 year, it's going to look like this.
Question.
I've got a terrible mix of colors here, but I think you see my point.
Right.
If you report in 1 year, what happens? They show you this room where this is an axe and a block of wood. They tell you to work on your resume, or I'll be back in a minute. Okay? If you report the blue, what happens? You better have a very good story. Everybody, every year, gets audited. They do not look at every well. They look at a sample of wells, a minor fraction of the total available. But if they come across and they see you reporting the red, they're going to do harm to you. They see you reporting the blue, they're going to want to know why. What happens if they see you reporting the little green that I put in there?
They keep a very close eye on you.
The little green is much too small. That never happens in the reserve sector. Why would you report your reserves too small then? Because you don't want to go in the little room with the axe. Okay? There were people who were reporting the red when shale first started. in the first year. That's what conventional reservoir engineering said. You report the well spacing. And so the first year, they reported 15 BCF. The second year, they reported 9. The third year, they reported 6. What do you think happens when your reserves go down by a factor of 3? Hello, I'm from the SEC. That's going to hit you where it hurts, doesn't it? Okay, we spent too much time on this. Yes, Jeffrey?
The outlines of the progressive propagation look really similar. Is that what actually happens? Because
we're not sure. I mean, we monitor this and we model this. Hear me again. We monitor and we model. One more time. We monitor and we model. What do we monitor? We monitor the installation. The installation is the hydraulic fracture treatment. We monitor that with Pinnacle technology, which is downhole microseismic, or we monitor it with surface microseismic, which is microseismic Inc., or we monitor it with Schlumberger's version of microseismic, which I believe is downhole, or we monitor it with EPS's version of microseismic. There's probably a half a dozen major vendors. Microseismic is the surface seismic people. What's better about surface?
you can calibrate the machine.
You can do that, and you can carpet bomb the surface with sensors. How many sensors do you get down below? Whatever you can put on a string. What's the problem with being on the surface? You're 2.5 miles away from what's happening.
You can't do combo.
You can. Very good point. And are they going to love you or hate you? Why? Because now you're using each other's technology, and they're going to be in a, how do you say it in Thailand, when people have a contest where there's going to be blood, you know, they will kill each other trying to prove their answers right.
Hey, that's good for me.
Only if you're the operator. Yes, sir.
Going to the surface and the downhole, how difficult of a correlation is it to put the two together?
It's not bad. I mean, they're geophysics people. Let's be honest. We're still ahead of the measurement, the measurements are ahead of our science for microseismic. I've heard people tell me that microseismic is black magic, it's this, it's that. When you're looking at downhole microseismic, depending on the distance that you are away from the receiver, there's a very clear field where it stops picking it up. There's a listening distance. Okay. There was a recent suite of, this is going to happen to you a lot of times in your career. I know it's a philosophical discussion, not an engineering one. But you're going to see a new technology come in, and it's going to be like wildfire. And everybody's going to rush one way or the other because nobody knows the answer. 2 years ago, everybody thought that the best practice in shales was to have a reduced rate, a low choke size. How did this come about? Not sure this is the exact story, but I believe it's true. Petrohawk had a well, they put it on production, they let it sit there, they basically forgot about it. Somebody left it on a 14 choke. They went back and they looked, and the well that was on a 14 choke produced better than all the other wells that had been on higher choke. Okay. Hence, the fantasy of reduced choke management occurred. Now, it started out lower, but it declined less steeply. So, and what you're seeing is you have a much higher rate and a much lower rate, and of course they cross. And then you start doing your EUR calculations 3 years into it, and they are the same. And so the myth of rate restriction has been reduced. Is it a good idea to do rate restriction? Probably so, from a variety of standpoints. One is geomechanical, that you're not stressing the rock. If you open it up, you can stress the rock. There are a number of cases when they first started producing shale wells, they were actually producing pieces of the reservoir. They were coming out of the hole, chunks of rock, because they opened the choke too wide. You're also probably listening better if you're on tubing, so possibility of that. You're maintaining your energy. But last night I had another email, third one in a row, from someone from, let's just say a super major in China. Well, I'll say it was China. And they're wanting to know if restricted rate is the way to go. Well, 2 years ago, there was a mad rush. All the papers, all the presentations, all the discussions, all the frac guys, all the production guys, all the completion guys. Restricted rate, restricted rate. Patience, time, looking at the data. Doesn't appear to matter. Now, there probably are some cases where it does. So if you're going to err on the low side. It's not going to be wise to err on the high side. Nothing good will come from the high side, except you'll get your money back faster. Sorry, nothing good from an engineering standpoint will happen on the high side. Okay? That went away. Same thing happened with microseismic. There's a theory right now that the microseismics are not the rock fracturing like this, but the rock actually relaxing and fracturing like that. So that's when I do my Yosemite Sam moment. All these years we've been talking about the microseismics being propagation events. If they're not propagation events and they're actually relaxation events, uh-oh. Now you're going, well, who cares? You're still picking up something. But what does it mean? Are the microseismic events representative of an open fraction? 3 letters, Dennis. G-O-K. What are they? God only knows. Yes.
Nobody tried to get a cube of rock somewhere and put it in your lap and...
It's been tried, but it's too small. Yeah. And there are a number of experiments like that, but it's too small. Sorry I finished your question before you asked, but he was asking, can you prove this? All right, sorry for the digression. Let's get back on the Pseudosteady-State. Okay, so we have this portrait of a reservoir pressure profile, and again, we decided this can only happen in a high permeability system. In theory, can this happen in a ultra-low permeability system? Sure. But how long will it take? Forever. And this isn't a 70s love song. Forever is a very long time. There's a well that I may give you that has been on production for 40 years, and it was in transient flow for about 12 to 15 years. It was out in a region where they drilled it, completed it, it was a fractured well. We just left it sitting there, producing. It's a beautiful case history. Took 15 years to get out of transient flow. Well, let's say 12 to 15 years. Dennis? Is that a long time? What were you doing 15 years ago?
And either starting middle school or ending elementary school.
Okay. So from that time until now, we wanted to know what the reserves were for this well. If I use the data from that time until now, will I over-extrapolate or under-extrapolate? Is transient flow stronger or weaker than pseudosteady-state? It's stronger. So what does that mean?
Over.
You're about to have a bad day. It will be a severe over-extrapolation. Okay. You extrapolate transient flow data, you're going to get a number that's too high.
Do we have correlations that, like, match?
What will happen, this is a really good point, is people will run model studies, and they'll calibrate off a model study, and they'll try to understand the behavior. But a model study it applies exactly to the case to which it was run, just so you know. All right. But now we've got enough data where people are monitoring things And if you can come up with a viable estimate of a benchmark, like, let's say a 6-month or a 1-year production, and then you have enough data to calibrate a recovery, an EUR, even though it's wrong, or probably is, I shouldn't say wrong. It's probably a little bit too high, but, well, it depends on how the analyst did it. But let's say that you've calibrated it and you believe your EUR number with 3 or 4 years of data is at least representative of a 30-year estimate. So then you can correlate a 1-year or a 6-month volume with a 30-year reserves estimate. And that's, you're going to see a lot more of that happening right now. You're going to see a lot of people trying to correlate early time performance with ultimate performance. The weakness in doing that is it has everything to do with how the well was completed, what the reservoir geology is, etc. Let me step away from that and come back and talk now about pseudosteady-state. We saw this graphic earlier today. I just drew it for you on the previous plot. But the first thing we're looking at is at approximately 2 hours, we have this profile. How was this simulated? This was actually simulated with a numerical reservoir simulator, which I wrote and I ran. And then at 291 hours, we have this profile. At 1300 hours, we have this profile. At 5800 hours, we have this profile. 12,125 hours, we have this profile. And you can see what I'm trying to show. These points here and here, that's your pseudo-steady-state. That's your dP, dr, RE equals 0. Okay, so the simulator did reproduce the correct behavior. Okay. This is a constant flow rate. Everything's cool. Right? Here's all the equations for that. I apologize. This is something that we will do in 620, something that's not necessarily important here. But these equations can all be derived for a circular system. Dennis, you've already done this. This is part of your assignment and your practice work. Is this hard? No. Is it algebraically intensive? Yes. And what does it tell you in the end? It tells you that you can recognize individual regimes. You can recognize transient flow, you can recognize pseudo-steady-state flow, and you can also write a relationship for the transition. Then how much transition is there for a circular reservoir? Virtually none. It goes immediately from transient flow to pseudo-steady-state, and you can see that on the previous graph as well. Okay. All right, so the next slide is, again, a reproduction, so to speak, of Lee's graph. And again, it's constant rate. So you can see the trends here. The corresponding points here, 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 and here, they're all from this equation. Okay. And they're the point about which it approximately becomes constant with the original or the initial reservoir pressure. Any questions or thoughts about this? We've already looked at this in a great deal today. Okay. Interesting? Probably not. This one is a random sort of it's not random, pardon me, it's a logarithmic linear decline. So in this case, time is on the log axis, rate is over here, and it's a straight line. Okay. So you can see it's bouncing around, and the rate's getting lower, so the pressure's getting higher, Q is going down, and the pressure's going up. Why did I do this, Dennis? Just to show that out here, the radii don't change. The pressure distribution changes, but the radii don't change. And this is a constant pressure case. All ALL of the history is generated with a pressure at a constant state. Okay. Dennis? still maintained? Can we have pseudo-steady-state for this case? Well, what's it going to be called? It'll be called boundary dominated flow because this is not pseudo-steady-state. The definition, and that's the problem, because we're talking about definition. The definition of pseudo-steady-state is that the pressure at all points in the reservoir, all points, changes with the same rate. Not for constant pressure. Okay. Now we project them on a Cartesian scale. Are these parallel? Neil? Bobby?
Yeah.
Good enough? Or are they really parallel? And you see where we're starting? We're at about 100 feet here. So that logarithmic scale thing, that was what was throwing us off. So pseudo-steady-state really does exist. Santa Claus. And here is the constant pressure case. And as promised, all the points are fixed wherever it is. I think it's actually down at 4,400. So they all come down like that. Are these parallel out here? Bobby? Not exactly, but is it close enough? That's the key. It's close enough. So for a given rate change, as long as the lines are sort of parallel, we're okay. So we just came out of the woods. We have pseudo-steady-state for a constant rate produced during depletion, and we have boundary dominated flow, for any other rate profile produced during depletion. What can we do with this? Nothing at the moment. Are we interested in reservoir pressure distributions then? No, because the only place we can measure things is at the wellbore. So everything that we do from now on, we will leave the reservoir and talk about the wellbore. So why study this? Just like I mentioned, we can only measure things at the wellbore. Is a simple model too limiting? And the answer is no. It turns out that the concept of steady state actually has application here. What's the radius of investigation? We talked about that. In our case, we use the probe radius formula. Other people use the impulse formula. Which one is more correct? I personally believe the probe radius formula is. How much difference is there in the coefficients? The multiplier. Practically none. So whether you derive it from the impulse or from the probe radius, either way it's okay. Why am I saying it's okay? You don't know any of these data within a fraction of the accuracy that you need to. So putting them in to an equation that has a coefficient of 2.4 or 2.39 is irrelevant. It absolutely has no, even if it was 2.1 or 2.2, it's no serious issue. Okay, this is material balance, and I think I'm probably going to skip this in the interest of your sanity and my time, because this is something you'll cover in 665 with Dr. McCain. I want somebody to read this for me. Sam, you're closest. You read it. And read it with conviction. Read it so that everybody on the radio can hear you.
It seems no longer fashionable to apply the concept of material balance to oil field. The belief being that it has now been superseded by applications of more modern technique of numerical stimulation modeling. Acceptance of this idea has been a tragedy and has robbed engineers of their most powerful tool for investigating the reservoirs and understanding their performance rather than imposing their wills upon them, as is often the case when applying numerical stimulation directly in history matching.
driller, reservoir, facilities. God only knows. Probably, production.
Reservoir, hopefully.
Facilities.
Sorry?
Facilities.
Okay, facilities. This guy, without being derogatory or vulgar or sacrilegious, is seen as a god. He wrote the 2 books on reservoir engineering. Whether they're the best books or not, I don't know. They're probably about the best we got right now. Probably need to have some more written. He wrote a book called The Fundamentals of Reservoir Engineering, which was a real lifesaver at the time it came out. And then he wrote this one as his career was closing, and he used that as an opportunity to give a speech. He gave a lot of speeches in this book, but this was one of my favorites. What's he saying?
Use your material balance equation, or I will hit you with a baseball bat.
Actually, what he's saying is that simulation is like your imagination. If you think about it often enough, it becomes reality. And he's got a point. You guys are going to be in positions of functioning with reservoir engineers, with simulation engineers. You may even manage some. You may even be a VP of a division that has to deal with them. It always comes back to the fundamentals. Everything that McCain told you is true. At some point, there's a thread that you pull that the whole thing unravels. And with a simulator, they have saved our bacon, so to speak. Shouldn't use bacon, but they have saved our behind a lot of times from giving us insight into these things. But don't ever believe it's real. An extrapolation off a simulator is probably a couple of years at best. I wouldn't make a 30-year extrapolation unless you just absolutely had to. What Dake is telling you here is there are fundamental relationships. What's the problem with using material balance? I already told you. You got to know everything about the problem in order to apply it. Isn't that true with a simulator as well? Yes, but with a simulator, you're using the computer program to make a prediction. What are you doing with a material balance equation? You're using a material balance equation to make a diagnostic or an evaluation of your data. If something's wrong inside of it, it may or may not pick it up. It may still give you an answer. That's the beauty of analytics, is they're not easily broken. But by the same token, it can give you the wrong answer. At any rate, we need to remember that simulation has a role. I'm going to say it that way and leave it there. Sam, did you get that out of it? Or are you going to become a simulation engineer? I often tell people that being a simulation engineer is the best job on the planet because nobody can tell you you're wrong. And here's all the material balance relationships. Again, I'm going to skip over this. All right, now I'm going to talk a little bit about wellbore storage, and some people have a good time with this, some people don't. This is an equation that is derived for wellbore storage. Nice, kind of a little flashy there. In this case, we're looking at the wellbore storage as being a rate. So you've got the Q, which is constant, that's here. And then you've got the Q sand base, which does this. Like that. That's how this works. And they are controlled by this coefficient, which is actually volume related for the filled fluid, and it's got some relationships to flow area or a rising or falling liquid level. Okay. So it's basically a volumetric coefficient. It's barrels per PSI. Okay. Then you have a time derivative with PWF and a time derivative with PTF. Happy you ready? I want to simplify that equation. It is a rigorous material balance on the system, but I want to simplify it. Give me a simplifying assumption that will remove a complexity from this equation. And for those of you that aren't paying attention, I'll note this. PTF is the pressure at the surface. PWS is the pressure at the bottom of the well. Now,
Can
can
we
you
relate
get,
PWS with,
sorry?
can we relate PWS with PTS, taking into consideration the pressure exerted by the fluid column?
Yeah, there are mechanisms to calculate that. Is it better to calculate or measure?
If you can measure it, that would
Of
be better.
course, but this is the beginning of the place where I'm gonna argue 1,000 times, if you're going to do something, measure the bottom hole pressure. Otherwise, you're calculating it, otherwise you're factoring error into your system. We know probably 90% of the pressure transient tests that are gonna be run in onshore North America, Canada, US, Mexico, whatever, they're gonna be surface pressures. They're not gonna spend the expense on it. So you're gonna have to convince somebody to spend the expense on it. Everybody ready for that? So we have a rate term, QSF, which we can never measure because we don't have the ability to do that. We have Q, which is the surface rate, which we can measure. We have C sub S, which is a multiplicative constant that represents the energy in the system, reservoir barrels per PSI. And we have the derivative of the bottom hole pressure and the derivative of the surface pressure. How do I make one of those derivatives go away? What's the quickest way to make something go away?
Make it zero.
Wrong, can't assume it's zero. Good guess though.
Constant.
If it's constant. The derivative of a constant is zero. So what we will do is we'll assume the surface pressure is constant. Is that true? Not exactly. Is it okay? We've been doing this for 50 years. Every time we have tried to reverse this problem and assume that all of those terms are non-negligible, we end up with an indeterminate system. Cannot be solved. So I'm just here as your guide. I'm not saying it's right or wrong, but we almost always assume that the tubing pressure is constant, hence its derivative is zero, hence we use a simplified form. Whether it is or isn't is between you and your maker. Alright, so what happens, as I explained before, is that for early time behavior, where the rate coming out of the reservoir is zero, you open the well, flush comes out, but there's almost nothing going on downhole. It's all coming out of the pipe. When we have a cylindrical tank, and we produce out of that cylindrical tank, what's the behavior of the height of the column in the tank with time? It's linear. It's exactly the same analog here. Okay. So when we open the top of the well, the first pressure is initial pressure, and then what happens? It drops linearly. And the same thing in reverse happens in the buildup. Except what's happening in the buildup? What happens when I shut in the well? Neil? No flow where? What happens downhole?
Still coming in.
It's still flowing. So as far as this thing's concerned, it's still flowing. So the first pressures are still representative of that shut-in at the surface is still flowing at the bottom of the well. So it's still picking up, it's not picking up a transient rate, it's picking up recharging that tank that we took the fluid out of. So instead of the pressure declining linearly, it's now increasing linearly.
What was the Q for the drawdown phase?
Sorry?
What was the assumption for Q in the drawdown case?
Q here is the surface rate. Its Q is equal and constant. And then QSF comes up from here. Like that. What happens whenever we shut it in? This is QSF drawdown. What happens whenever we shut it in? The well continues to flow. What's this green called? Called afterflow. Okay. Can we measure QSFDD and QSFBU? Dennis?
Not accurately.
We can drop a spinner down there, some kind of device down there, but it's not going to be accurate enough to use for reservoir stream calculations. So what do? We assume away everything we can. And in our case, we're going ahead and assume the tubing pressure is constant. That kills a major piece of it. Yes, whenever we assume that the tubing pressure is constant and that derivative is zero, we knock off a major issue. Okay, so what's the slope here in wellbore storage? QB 24 CS. What's the slope here? Same thing. Or do we have something else to think about? They should be a mirror image of each other. Is this on the test? You can bet your life on it. Is it going to be this clear? I hope. If you were me, would you give the class real data or synthetic data?
Real.
You're not me. You got to be me.
Real data.
Why? Because real is confusing. Real is annoying. Real is real. Well, that's probably a good quote. All right, Jeffrey. You're next. This is an approximation that we derived lesson 20-something in 620. And what I did was I decided to try to solve the issue of wellbore storage. Early time wellbore storage is here. This is your wellbore storage region. And then this is your transition region where you can't analyze anything. So I created a single equation which approximately represents that. What value is this equation? You would like to know PSD. You would like to know PSD. You would like to know PSD. You do know PW, you do know T, and you do know CD, or you know their equivalent in real variables. What happens when you solve for PSD? That's deconvolution. Okay? There's a model specified, so I think I might be butchering the purity of the vocabulary, but that would be a process of deconvolving the data, getting the true underlying model from its components. Sorry, somebody had a question. Dennis, what would a single-term exponential expansion look like? What's the single-term expansion for EXP class? EXP of X for X less than 1 is approximately equal to what? 1 plus X? Okay. So if we do that here, X is equal to TD, TSD, CD, right? PXP is going to be. It's going to be, this term is going to be approximately 1 minus TD over PSD CD. What happens when you put that in? The blue stuff is going to be for that, sorry. That's an extra long stuff. Okay, so that's 1 minus 1, which is? And then that's minus a minus, so that's TD over PSD TD, that reverts to TD over CD. Someone tell me where TD over CD is on this plot. It's right here. This is PWD approximately equal to TD over CD. Okay? So you at least get that characteristic behavior. And then what happens at long times for the exponential? What happens? TD gets to be large negative number. What's the exponential of a large negative number?
0.
1 minus 0 is? And multiplied by PSD. So here's your PSD curve. Now, if this had been a perfect match, and I'm just saying if, and we had captured this transition region, then this would have been a game changer. We would have been able to analyze the transition data in terms of reservoir properties. I told you before, in theory you should be able to do that, but in practice you can't. So it's just a nice set of remarks here that, you know, we've got a model that represents both ends, but not exactly the middle. There is a more complicated model that does match both of these things, but I would not recommend using it as some sort of an inversion tool to estimate the underlying ESD function. I know this is about as abstract as anything I've ever done in this class, but I just want you to realize that when it comes to wellbore storage, there's no shortcuts. This is actually a map of all possible wellbore storage solutions. Somebody remind me again, what's the assumption on this page?
The QSF equals to 0 and
PTF is equal to a constant. The QSF equals 0 part is over on the left-hand side. The QSF equals Q part is over on the right-hand side. You're exactly on par. Is that what you're trying to say? This is QSF equals 0. This is QSF equals Q. Is that what you're trying to say?
No.
Well, that's what you meant to say, if you had been thinking. Homer, you okay with this? This is making me want to be a driller more and more, isn't it? But someday when you have your big cowboy boots and your Cadillac, you know, and your ex-wife and your future ex-wife, you'll think back about everything we talked about. And you say, Tom told me there was going to be an ex-wife here, a transition zone, and then a new ex-wife there. All right? You good with that?
I've been told that petroleum engineers are able to afford up to 4 ex-wives.
Yeah. Well, that's only if you work overseas. I encountered one of our undergraduate students, and he told me his life story, and that he's the product champion. I won't say what it is, you probably track him down, but he's been in Russia for over 10 years. And I said, why in God's name would you be a product champion in Russia? And it's not what you think. That is part of the story, but it's not what you think. He had a divorce, and his wife kept suing him for more money. So he just decided to stay overseas permanently, and all of her lawyer's letters just end up in a stack, right? Yes, of course, he's also found it. There are benefits to being single in a place like Russia, so I probably wouldn't recommend it.
10 years, so he really cool.
No.
No, but the thing is, you have to be married for a certain amount of time for her to be able to sue you over and over again for more and more money.
Not from one of my experiences. If you're in the correct state, not Texas, but Texas I think now has an alimony clause or some sort of support clause.
Yeah, it's like, but it's 10 years for.
See, you've lived in California all your life.
Yeah.
Bad things happen to people there. My aunt and uncle lived in California, and I'm not exaggerating. She sued him for 30 years. Every time she thought he worked overseas just like this guy as a driller, and he squirreled his money away everywhere you could think. He was a pack rat, you know. Everything you could think of, he put his, you know, he bought carpets, he bought gold and stuff like that, you know. He's gone now. He was a very interesting individual. Before 2001, he had to re-enter the United States by crossing at a convenient border, not presenting his passport. You didn't have to then. I can remember going across and they'd ask you who the president was, and I'd always say the president of Mexico. I was going into a government facility one time, and right before we were entering, our host said, "Hey, all you guys are American citizens, right?" And I said, "Stop." He goes, "That's not funny."
What was the ESD?
It's the pressure of the non-wellbore influence case. It's just it's a dimensionless pressure, so it's a delta P. It implies that it has skin but no storage. So it's the underlying root model. Okay, this is the so-called Bourdais Greengarden type curve, and Greengarden is credited with publishing the first version of this, which was the solid line. Bourdais is credited with publishing the second part of it, which is the dashed line, or the derivative. And I don't know, knowing Dr. Greengarden's ego, I'm surprised it's not the Greengarden-Bourdais type curve. It probably is, and I just say it wrong. Bourdais now gone. He's also the guy who formulated the derivative formulation. He's got a textbook floating around. It's like $300 a copy, so maybe you might want to look for the illegal PDF version in Indonesia or something like that. It's not a bad book. It's useful for understanding different reservoir models and that sort of thing. But what you're looking at is all we're going to cover. I'll show you other ones. Well, I shouldn't say it's all you're going to cover, but we might do the fractured well case, but probably not. So these dashed lines are the derivative, and the derivative is defined as TD, dPd, dTd. Okay, that's the PD prime function. Okay. So why did we use that definition, Avi? What are the units or the dimensions of this? It has the unit or dimensions of what? And I know I'm butchering this. Of PD or pressure, right? PD or pressure. So that means we can plot them on the same graph on approximately the same scale. And this was very important to me. So I'm looking at this, and I'm thinking, you know, if I'm going to have two functions on a graph, I damn sure want them to plot nearby each other. And if by reformulating it slightly, I can make them plot very close to each other, that becomes a really powerful way of doing things. I'm not sure that's what Bourdieu had in mind. Because what Bourdieu and others had noticed is that using this definition of PD prime, the derivative is horizontal for the logarithmic case. So if the definition is PD is equal to 1/2 natural log 4 over e to the gamma TD plus S, now take the derivative of that. Okay? That PD is equal to 1/2 natural log 4 over e to the gamma plus S plus 1/2 natural log of TD, right? What's the derivative of this term? So that's dPD, dTD. What's the derivative of a constant? So that first term is d by dTD of 1/2 natural log 4 over e to the gamma plus the derivative of the spin factor plus the derivative of 1/2 natural log TD. What's this one? 0, 0,
1 over TD.
and then 2, well, 1 over 2 TD. Yeah. So this becomes d PD dTD is equal to 1/2 of 1 over TD. So I'm going to be lazy, and I'm going to multiply both sides by TD. Sorry, my brain didn't engage on that one. My apologies.
Just 1
So what happens when I multiply 1 over TD by TD? And the final answer is PD prime is equal to TD, dPD, dTD, and that is equal to 1/2 for radial flow. Because this is the radial flow.
When was this result published?
What year were you born? What year were you born? What year were you born? Yes.
87.
90.
84.
84. Man, I got socks as old as you. What about back row?
77.
Sorry?
77.
77?
Yep.
Holy, man. You're an old man. What'd you do with your life?
I'm back to school.
You mind if we start calling you Abuelito?
That's fine.
Little grandfather. Okay. So, there was a battle. And about the time you were born, a fellow by the name of T.O.B. with his advisor, Anil Kumar, published a paper on derivative behavior for fractured wells or something like that. Then Bourdieu published something on derivatives, and I told you that I came across a guy from Schlumberger who also said he was doing derivatives to establish drift on gauges. He was a flow control engineer. So all around probably 1977 to 1980, there are probably at least 4 or 5 people that claim they had done this. You go back and check the literature, and this stuff was being done in the 50s, but everybody turned their back on it because they didn't know how to take a derivative in the 50s. So they had a war over this. Who invented it wins, because they all wanted bragging rights. There's nothing new. I want everybody to listen to me. My student and I in 2008, I derived this thing called the power law exponential. I did it from observation. I didn't break my arm, pat myself on the back, but I was pretty proud of myself. I'm not going to lie to you. Still, the student found it in 1942 papers.
people, okay.
Didn't have any way of using it because it was too complicated. Same thing happened, I developed the Muscat method for estimating reservoir pressure from buildup tests. I said, this is a stupid approach because you had to guess. It was, there were too many unknowns. So you can eliminate this by taking the derivative. So I took the derivative, formulated derivative relationship. I was presenting the paper when somebody mentioned that Arts had done this in 1949. His plot was upside down, his derivatives weren't expressed right. Who cares? It's the same thing. I already told you my experience with the pressure integral. 3 of us presented within a month of each other. None of us had any knowledge of what each other was doing and how the hell we came up with the same thing at the same time. It was a complete mystery to me. All these guys are fighting over who gets to claim it, right? Until somebody went back in the literature and found out that the hydrogeology people had been using this function in the 20s. So they began calling it the Chow derivative group because it was some guy named Chow who had been using it in hydrogeology or hydrology back in the 20s and 30s. It's just math, people. You can't patent a math equation. Okay, everybody does, but you're not supposed to. It's inhuman. It's unfair. Sorry, go ahead, Sam.
What were the different values of the concordance?
We'll come back to that in a second. Any other closure comments? Yes.
The point of my question was that this looks a lot like the well test derivative. Which one was the chicken, which one was the egg?
This is the well test derivative.
Right, but
this is a tight curve. This is all the possible solutions for this case. In this case, what was used to generate this was the complete model. It included wellbore storage, it included radial flow, and obviously it included transition. So this is the model plot, not the data plot. All possible solutions are on this graph. So Sam, number 1, asked the question, what are those numbers along the side of the thing? Those are the family parameters. How many things can you plot on a graph, Ani? You've got 2 axes on a 2-dimensional piece of paper. You've got 2 axes. So you can plot what is dimensional pressure proportional to? Permeability. What's dimensional time proportional to? Well, whatever the variable of interest is. In this case, it's the storage coefficient. Okay. So we have wellbore storage, or we have dimensional time divided by wellbore storage coefficient, which becomes time divided by storage coefficient. And then we have dimensional pressure, which is directly proportional to permeability. So you slide the graph up and down, that changes the permeability. You slide it side to side, that changes the wellbore storage coefficient. Now, you can have a third parameter, because you've got multiple curves. That's called the family parameter. What's the family? The family is C, D, E to the 2S. Why is it 2S? You can see it. Because it's PD is equal to 1/2 natural log 4 radius gamma times PD plus parentheses plus S. So when you multiply that by 2, you get 2S, raised to power, or exponentiated. That's where your e to the 2S comes from. Okay. Grignard deserves a wallop of credit for figuring that out. It seems trivial now, it's just algebra, but it was a very clever move at the time. Rainey, who was his advisor, had taken this directly from the hydrology literature and also from chemical engineering. So the curves that Rainey published in the 60s and 70s were all pressure and dimensional pressure and dimensional time, no storage coefficients, etc., no derivative, blah, blah, blah. And then, Grignard came along and normalized it with dimensional wellbore storage coefficient, CD, and he collapsed it all into curves. What about using an integral? Yeah, we gotta go.
Dr. McKay,
Yep.
what did Bourdain do? What did Bourdain do?
Bourdain did derivative.
So the speed of your transition zone that depends on your scale factor.
Yes, exactly. I'm gonna log off this. Do your thing. log in. And you may want to do the same thing. Do you have a big profile? When you log in, does it take a long, long time? Merle, will you take care of it? Oh, yes, thank you. I didn't use him when I didn't need them.
And my biggest collection I think. And I guess they haven't been find the correct version, but it might come along. I can't tell you this afternoon. Unfortunately.
Do we get class off today?
What?
Is today a holiday somewhere? Probably somewhere, but.
There we go.
Okay.